All right, so continuing from last week, we finished off talking about some applications of Bernoulli's equation after we derived Bernoulli's equation. And we had a few different devices, and we talked about different kinds of pressure within Bernoulli's equation depending on the form that we wrote it in. We could write it in the form of pressures. We'd have static pressure, dynamic pressure, and stagnation pressure, which was the combination of our static and dynamic pressures. We defined what stagnation pressure means. It really just means the pressure of a fluid when it is brought, or when the velocity of that fluid is brought to zero. So you have a moving fluid along a streamline. If we slow down that fluid without disturbing the streamline, still steady state, and bring the velocity to zero, we have something called the stagnation pressure. Just to answer the question from the chat, the first half of this lecture is the material on the exam, and second half will just be moving forward. This first half of the lecture will be related to exam material, yes. Yeah, there will be some material from this on the exam. But a lot of this will be reviewed from Thursday. Then we introduced one of the flow devices, a measurement device called a pitot tube. And a pitot tube measures your stagnation pressure. And then there's also a pitot-static tube or pitot-static probe, which measures both the stagnation pressure and the static pressure. And by reading both of these things or measuring both of these things, you can calculate the velocity of a fluid flow. And this is a common device that's on aircraft to calculate their airspeed. We calculated or rearranged to find the equation for the velocity of a fluid using a pitot-static tap or pitot-static tube. More examples. The next device we introduced was called a bell mouth inlet. And the special thing about a bell mouth inlet is it's another flow device, but it essentially has no losses and no slip out the wall for a short period of time. And we calculated the velocity flowing through a bell mouth inlet as a function of the atmospheric pressure and the pressure at some tap. So the difference between this and a pitot-static tube is this is open to the atmosphere, so we're measuring static pressure as our atmospheric pressure, and the pressure tap would be PV. Next, we look at the Venturi meter, which is a section of pipe that is a convergent, and then a divergent section. So it narrows down to a throat and then expands back out to the original dimension of the pipe. And if we measure the pressure at various regions, we can calculate the flow and the volume flow rate because it is an enclosed volume. And then we developed an equation for the ideal flow rate of a Venturi. So the flow rate is just equal to the velocity of the fluid times the area. And we can solve for that velocity as a function of the difference in pressures and difference in areas of our fluid and our geometry of our Venturi meter. And this we called our ideal flow. Sometimes, very rarely, we have flow that is equal to our ideal flow. There are some losses, although they might be minimal. And so we can introduce a Venturi or discharge coefficient, which is our actual flow rate divided by our ideal flow rate. And so if we take our ideal flow rate and we multiply by our discharge ratio, we can get our actual flow rate, which is this equation here. So of the flow coefficients, the discharge coefficient is the ratio of our Q's. So CD is equal to Q actual over, we can just say Q over Q ideal. Velocity coefficient, CV, is equal to V over our ideal velocity, which would be if there's no losses. And then C, we could see kind of an example here would be the area of the actual flow exiting some device divided by the actual area. So we said for a Venturi meter, typically the discharge coefficient is around 0.98 for moderate flows. Then we did an example, solved for the flow rate of a Venturi meter. We did another example where we used continuity equation and derived an expression for the mass flux or mass flow rate. So this takes us to where we are today, which is an orifice meter. So an orifice meter is another flow device where the characteristics of flow through some restriction is known. And if we measure the pressure on either side, we can get information about the flow rate and the velocity of that fluid. So let's define an orifice. An orifice is just some restricted opening through which a fluid flows. So if we know the geometry of the orifice and its properties of this fluid allows one to measure a flow rate. So properties of the orifice itself and fluid allow us to measure Q, which is our flow rate. So there is some contraction in the flow just downstream from the orifice, so that's here. So this would be part of our contraction ratio. So our orifice has a diameter or an area A0, but then our actual flow, once it leaves here, we follow the streamlines. Streamlines from the edge of that orifice some distance after will reach a minimum before it starts to expand again. And that we call AV. And we can write the contraction coefficient for the orifice is equal to AV over A0. So this is because after some distance, the flow contracts from A0 to V. So A0 is the area of the orifice. And AV is the minimum flow area. So usually from experiments and theory, CC will, or the contraction coefficient will be somewhere around 0.6. So if this is the case, here's just showing an example of two different openings. We have one as a sharp point and one is a square edge opening. So if we use our definition, we can write A2 is equal to our contraction coefficient times A0 for some other point down in the flow. So let's assume we have 0.2 down here or 0.2 down here, and this area here is A0. And if we use our equations that we derived from a Venturi, so from our equations of flow through a Venturi, then we get Q is equal to CV times CC times A0 times 2 times pressure at 1 minus pressure at 2 divided by a rho times 1 minus CC A0 over A1 all squared. And then finally, this whole expression is the power of 1/2. So this is if we had some pipe, let's say, like this. This would be A1. Let's assume it's a continuing pipe. The diameter of the orifice is A0. And at some point before, we would measure the pressure. And at some point after we would measure the pressure, we know our contraction coefficient, we know the area of the pipe, and we know the area of the reduced orifice. And we can calculate the flow rate through that orifice if we know the contraction coefficient. And then all we have left now is this velocity coefficient. So if we look over here, right at the top screen before we finish this page, the discharge coefficient is just the product of the velocity coefficient and the contraction coefficient. So as I was saying, our discharge coefficient is just our velocity coefficient times our contraction coefficient. Discharge, think of this as related to Q, this is related to V, this is related to area. So contraction is the ratio of our area change, velocity coefficient is the ratio of our velocity change, and the discharge coefficient is related to our flow rate change, which is Q, and Q is equal to V times A, so CD is equal to CV times CC. So if we substitute this into our equation up here, we can write this is CD. So our equation then becomes the flow rate through our orifice meter or our orifice flow device is equal to CD times A0 times 2 P1 minus P2 divided by our density of the fluid, rho, times 1 minus our contraction coefficient squared, times the area of our orifice squared, times the area of our pipe squared. And this is all to the power of 1/2, or all square rooted. So if we have an orifice device, we could use this instead of a Venturi to calculate the flow. It's usually just a thin plate, and it's quite easy to install and cheap. But because it involves much more mechanical loss, if it's expensive to have a mechanical loss in some pipe flow, then it might not be too ideal. But if you don't care too much about the losses, this is a great mechanism, great, cheap, and inexpensive mechanism for measuring flow rate. So let's do an example. So actually, no, let's look at some special cases where we have an orifice leaving, say, a tank. So maybe it's not a pipe. The equation for the velocity exiting at this point, derived from Bernoulli's equation, just like we had from before, would now just be our velocity coefficient times 2g times the difference in our pressure. So the pressure at the surface minus the pressure at point 0 divided by gamma plus the change in elevation Zs minus Z0. To answer where the square root comes from, if we think of Bernoulli's equation, remember Bernoulli's equation from before, P over rho plus 1 over 2, or sorry, V squared over 2G plus Z is equal to a constant. So all we're doing here is looking at this streamline. The velocity up at the top is 0. And so we're writing up Bernoulli's equation and we're solving it for V0. And we would find an ideal V0. And if we multiply that by our velocity coefficient, we have our actual velocity from that flow. And then if we multiply by the area and we include the area coefficient, the contraction coefficient, we have CV times CC, and we get our flow rate in terms of our discharge coefficient, the area of that orifice, and then the pressure at the orifice opening minus the pressure at the surface of our reservoir tank times the elevation change. So these equations are all derived from Bernoulli's equation, and then we're just rearranging based on some things we know along the streamline and solving for the unknown that we want to find out. And then we can also get some other equations, another set of equations if we consider the continuity equation, which just means that the flow rate along a streamline is constant. So Q at some point is equal to Q at some other point. So if we have a really large reservoir, we can apply Bernoulli's equation if we assume that the rate of change of the fluid level at the source of the reservoir is negligible. So we might have to calculate maybe how long it's going to take for this to empty, but we would still consider the velocity at the top surface as 0. And then we would use our continuity equation to account for the flow out of that reservoir and the volume change of the reservoir. So let's look at this example. In this example, we have compressed air is used to force water through a 25 millimeter diameter orifice. That's over here. So we have A0 is equal to 25 pi times 25 squared over 4. And that's millimeters squared. The water level in the tank is kept stable by adding water at the same rate at which it is being discharged through the orifice. And it doesn't tell us what this is. The orifice has rounded corners, and the manufacturer's literature indicates that the discharge coefficient is approximately equal to 0.94. So we have CD is equal to 0.94. Under a particular operating condition, the gauge pressure of the air above the water surface is 300 kPa. And the water surface is 1.2 meters above the centroid of the orifice. So ZS minus Z0. Difference in elevation is 1.2 meters. So finally, and the temperature of water is 20 degrees C. At what rate must water be supplied to the tank to maintain a steady state condition? So let's go through this example and help explain the flow rate equation for an orifice and how we would get this work. There's one connection we need to make before we can solve this, and that is relating the Q in and the Q out. So if this is steady state, like it says right here, that means that the reservoir or that tank is not filling up and it's not emptying. So it's maintaining constant volume of fluid inside. So in this case, our continuity is just that Q in is equal to Q out. So let's write our equation for discharge from a reservoir. So Q out is equal to CD times A0 times the square root of 2 times gravity times pressure at the surface minus pressure at the orifice divided by gamma. In this case, we have water plus the surface elevation minus the elevation at the orifice. So we said our CD is 0.94. Our area is pi times, if we do meters, what is our area? 0.025 squared over 4 times the square root of 2 times 9.81 times the pressure at the surface is 300 kPa. What is the pressure at the orifice? What is our P0? Any ideas? Yeah, it's our atmospheric pressure. So right after the fluid leaves, that's the pressure we're considering. Just after it exits the orifice, that fluid is exposed to the atmosphere, so our pressure is atmospheric pressure. And since the pressure that's given to us is a gauge pressure, we're considering the atmospheric pressure is a 0, so this is equal to 0. So we just have 300 over our specific weight of water, which is at 20 degrees C, 9.79 kilonewtons per meter cubed. And our change in elevation is 1.2 meters. So we have consistent units with this, and we would get 0.01153 meters cubed per second, which is also just equal to 11.5 liters per second. So for change in elevations, Z1 and Z2, if we draw a diagram here, let's say our reservoir is this. Here's our fluid. We have our pipe Q in. So our distance to the orifice and our distance to the surface is this. So then just our difference in elevation will be Z surface minus Z0, which we know is 1.2 meters. At the top, we have pressure at the surface. And out here, we have pressure is equal to P atmosphere. So that's all that diagram would look like. So let's look at an example now where we have a draining reservoir. So now we don't have a steady state system. The orifice is being used to drain some reservoir, and this question is looking at the diameter of the orifice that's required to drain this pool completely in 2 hours. So it says that the pool's dimensions, 12 meters long, 6 meters wide, and it's filled 2.5 meters deep. We have a drainage outlet, which has a discharge coefficient of 0.7. So CD is equal to 0.7. Determine the diameter of the orifice. So we want to figure out basically A0 so that we can drain the pool in 2 hours. So we're also given length, width, height, CD, time, 2 hours. We can write this in seconds, 7,200 seconds. So if we look at our pool system, let's just redraw it from the side. We have our hole in the bottom of the pool. We have our fluid leaving. Let's measure this distance as the height of our pool, or the current height of the fluid in the pool. And so we know that the flow rate, so the Q out, must be equal to the rate of change of volume. It's a volume flow rate. It's volume per second. So this is equal to the volume of the pool, the rate of change. So d dt of the volume of the pool. The volume of the pool is length times width times the depth, h. And the only thing that's changing with respect to time is that h. So this will be length times width times dh dt. Now there's one thing that we need to add here. This would be true if we were filling up our pool. So this is actually going to be equal to negative because we're draining our pool. So let's write our equations. We have negative dh dt times length times width is equal to q, which is equal to cd times a0 square root of 2g times p1 minus p0 for gamma plus z S minus Z0. So this is our equation we're trying to solve. So how can we simplify this? What are some terms we can get rid of here? So this is a pool. What is P1? Or I guess we could call it P, the surface. P0 is 0, yeah. What about P1 or P surface? Yeah, P1 is also atmosphere. So PS equals P atmosphere, P0 equals P atmosphere. So this term here goes to 0. This change in elevation from the surface of the pool to the orifice is just h. That's our dimension for height. So all we're left with, CD A0 to GH. And then this is equal to negative DH T LW. So there's a question in the chat, how do we get this term on the left-hand side here? Where is our velocity term? Well, when we derived flow rate back at the beginning of lecture 6, I think, maybe at the end of lecture 6, we said flow rate was the volume of fluid for a steady state moving through some control volume or some fixed volume. So that was equal to the velocity of the fluid times the area, cross-sectional area that fluid is moving through. And that would be the flow rate through some cross-sectional area. Flow rate units is meters cubed per second. So it's amount of volume per second. So we know that the volume leaving the pool per second must be equal to the rate of change of the volume of liquid in the pool. So the rate of change of volume of liquid in the pool is equal to the derivative, the time rate of change of the volume of the pool. So since the length and width are constant, the only parameter that's changing is h. So we have dH dt times L times W. So we have this equation, and we're asked to figure out how much time it takes to drain the pool. So we have to rearrange and we have to integrate. So what we can do is we can multiply both sides by dt, and we're left with negative dH times, and we move the square root of h on the left-hand side, so we have over square root of h is equal to, we'll move all the other terms to the right, CD A0 divided by L times W times square root of 2G times dt. So if we integrate the left and the right-hand side, get 0 to h of, or I guess not from 0 to h, we're going from a height of h to a height of 0, because we're draining the pool. And then all of these terms on the right are constant, so we can integrate just the last term, 0 to t. And if we do this, we get the equation 2 times the square root of h is equal to CD A0 square root of 2g divided by length times width times time to empty. Let's just define T empty is up here, so it's different than T. So we know all those values. And we need to just rearrange for A0. So if we do that, we get A0 is equal to 2LW over CD times the square root of 2GTE. I forgot square root of H. And if we substitute the definition of area as pi times D0 squared over 4, we get D0 is equal to square root of 8L W root H divided by pi CD times root 2 GTE. And then finally, our diameter would be equal to 0.144 meters or 144 millimeters. So the negative sign is canceled because it's one of the questions of the chat. How do we get rid of this negative sign over here? So when we're integrating, our state 1 is when the pool is full. So we're integrating from H to when it's empty, H0. So we'd end up with this side evaluated from 0 to H. So 0 minus that H term times a negative, it ends up being a positive value. We can just think of D0 is equal to, how we got D0, A0 is equal to pi D0 squared over 4. So that's all we did to substitute there. So that is a pool flowing from, or just a reservoir that is draining. We're trying to calculate the drainage time. And basically, this is our equation for a reservoir draining. And you can rearrange that however you want to find the terms that you need. This is assuming that the drain is at the bottom of that reservoir. So let's level up a little bit and see if we can do this problem. So in this question, we have two compartments now inside a pressurized tank. So the surface of both sides are pressurized. And in the source reservoir, so the left-hand side, call this source. The air pressure is 500 kPa. And the depth of water above the centroid of the orifice is 1.7 meters. So in this case, we'll just choose Z, our surface, or our 0 for Z would just be the height of the orifice because we don't really know how high that is off the bottom of the tank. So we'll just compare everything to our orifice. So we say Z0 is equal to 0, just to make things easy. So let's keep going in the question. Discharge reservoir. So this is our discharge side. The depth of water is 2.3 meters. That's, I'm assuming, with respect to the orifice. So we have ZS2 is 2.3 meters. And the tank contains inflow and outflow ports to maintain steady state conditions of the two compartments. So if it's steady state, that means, as we looked at here, the flow rate Q and Q are the same going in and out. Temperature of the water is 20 degrees C. The discharge coefficient of the orifice is 0.87. What air pressure must be maintained in the discharge reservoir so that the volume flow rate through the tank is 10 liters per second? So we're looking for P2. And we know that Q is equal to 10 liters per second, or we could write this as 0.010 meters cubed per second. So is there anything we're missing? The only thing we're missing I didn't write down is the actual size of the orifice. So it says the diameter of the orifice is 50 millimeters. So D0 is equal to 50 millimeters. So A0, the area of that would be pi times 0.05 squared over 4. All right. So we have all the information we need. This problem is really mostly difficult because it just takes some effort to extract all the info. But once we have the info, all we really have to do is use our equation and just substitute in the right values. So if we look at the equations for flow through a submerged orifice, we can rearrange our equations for velocity and our flow rate using the exact same equations before. The only thing that's changing now is the pressure on the other side of the orifice and the Z height of the other side of the orifice. So before, this would be the depth of our orifice. Now this is going to be the pressure of the surface on the second side of the reservoir and the depth of the other side of the reservoir. So that's the only thing that changes. And we can rederive these from Bernoulli's equation, but these are essentially the exact same equations. We just have different versions now. So we go back to our example. Let's use our equation for Q. Q is equal to CD times A0 times the square root 2G times PS1 minus PS2 divided by gamma plus ZS1 minus ZS2 for flow from 1 to 2. So we have all these values, 0.87. Our area was pi times 0.05 squared over 4. 2 times 9.81. Our pressure on the reservoir side, PS1, was 500 kPa. We're trying to find PS2. We're not alone in that. Our specific weight of water is 9.79 kilonewtons per meters cubed. And then we have our ZS1 was 1.7, and our ZS2 is 2.3. And our discharge was 10 liters per minute, or 0.010 meters cubed, liters per second, or 0.01 meters cubed per second. So solve for PS. And we get 159 kPa. So what this is saying is if we wanted this system to maintain equilibrium, given those fluid level heights, we would need the pressure in the second tank at the surface to be 159 kPa. So I didn't go through the derivation for these equations, but they're so similar to the other orifice, flow-through and orifice equation, and everything is derived from Bernoulli. And our continuity equation. The only difference to remember is these terms here. That's the only difference. So if the pressure on the other side of the orifice is not draining to something that's open to the atmosphere, we can consider the pressures by this. So another question, what is the delta? Where do we see delta? The delta on the diagram. This diagram? Do you mean this at the surface? Oh, delta H. This is just showing the change in height. So we could say delta H is equal to ZS1 minus ZS2. So if we know the difference in the elevation between those two reservoirs, then that can give us our delta H. So the last section before we're, the last two sections before we finish up is looking at viscous effects. So we talked about how Bernoulli's equation does not work when we have losses due to friction, and we need steady, incompressible, and inviscid flow. So inviscid flow is not really common or possible, especially when we have flow through ducts and pipes. We're going to have some sort of losses. So if we go back to Euler's equation, we think way back to the beginning of lecture 7, we derived Euler's equation. This was an equation for the forces acting on a fluid element. If we include the force of friction due to the shear stress of a viscous flow, we get this term. So this is our viscous term. So if we now assume that we have steady and incompressible flow with some losses, we can then just integrate the left-hand side from point 1 to point 2 along a streamline. And we have Bernoulli's equation still, but modified to account for friction loss. So friction due to viscosity. So here, the value of P in this equation, let's just write it out here, T PL over gamma times A. P is the perimeter of the pipe. L is the length or characteristic length. So the distance apart from point 1 to point 2. And then our area is the area of the pipe or the duct. And then tau is just our shear stress, and gamma is our fluid velocity. So tau is our shear stress at the wall of the pipe. So if we have a closed conduit and we have no change in our velocity, so our area is constant and our flow rates are constant, so our velocity isn't going to change, the friction is only going to contribute to a loss in pressure of our flow, and we can call that loss of pressure our wall friction head loss. We can write it in terms of pressure head, and our pressure head due to friction, or our head loss due to friction, is just HF. And it's equal to the average shear stress along some length of pipe with perimeter P and area A at the wall. And it's equal to tau 0 is the shear stress at the wall. And then we're rearranged with this equation here, where we have the change in pressure from P1 to P2 plus the change in elevation from Z1 to Z2 is equal to our head loss. Or if there is a change in those things, if they don't equal each other, then we can attribute that loss to our pressure head loss. So let's look at an example with friction head loss. In this example, we have water at 20 degrees C flows at a rate of 40 liters per second in a 200 millimeter diameter pipeline, where the pressure and elevation in a particular section are 480 kPa and 10 meters respectively. If the pressure and elevation at a section 50 meters downstream, so we have a long distance of pipe now, 50 meters away, are 400 kPa and 15 meters respectively, estimate the friction head loss and the average shear stress on the pipe between the two sections. So let's go back to our equation. We can write P1 over gamma plus Z1 minus P2 over gamma plus Z2 is equal to our friction head loss. So where do we go from here? P1, section 1 is 480 kPa and has an elevation 10 meters. P2 has a pressure of 400 kPa and has an elevation of 50 meters. Sorry, 15 meters. So we substitute this in. Gamma for water is 9.79 kilonewtons per meters cubed. So we have 480 over 9.79 plus 10 minus 400 over 9.79 plus 15 is equal to HF. And I don't have the solution in front of me. Who has the who can calculate that for us? So it should be in units of meters. So is this 33.17 meters? $3.17. 33 seemed like a lot. 3.17 meters. So that is the head loss. So what that means is if we had a pipe and we had a pressure tap at the two sections, the pressure head on an open tap to the atmosphere at some point would be here. Let's draw this a little better. So that'll be our pressure head at point 1. And then sometime later, our pressure head would decrease. So when we talked about pressure head, this is what we're referring to. Just if we had an open tap, we want to visualize this. If we had a bunch of open taps along that flow, the pressure head would be our hydraulic grade line, and that would be changing depending on our pressure and our elevation, and any losses. So the next part of the question is to find the average shear stress, I believe. The average shear stress in the pipe. So if our frictional head loss is equal to tau 0 times PL over gamma times A, our perimeter is pi times D. Our diameter is given as 200 meters. Millimeters. Our length is 50 meters. And the area is pi d squared over 4. So if we substitute this in, we would get T0 or tau times L over gamma times D, and this is all over 4, so this top part is multiplied by 4. So we know everything. We're just solving for our tau 0. And we would get HF, which is 3.17 times gamma, 9.79, times diameter, 0.05, times 4. Or sorry, not times 4, divided by 4. divided by 4 times 50. Yes, so on the diagram, to answer the question in the chat, this distance here would be our head loss, HF. So who can calculate this? So P divided by A, the pi times D divided out, so we're only left with the D over 4 in the denominator, so we have 4 over D in this equation over here. So 0.007758 is the answer I get. And what would be the units for that? This is in kilonewtons. So we'd have kilonewtons per meter squared. So that would be kPa, I believe. So we can write 7.758 pascals. So yeah, when we talk about the pressure heads, the hydraulic grade, this whole quantity here is H1. This whole quantity here is H2. So the Z values are not equal to H1 and H2. The Z values are the physical elevation of the pipe. The pressure head would be the sum of the elevation pressure and the static pressure of the fluid flow. So if we were to open that up through a pressure tap, instead of a pipe going straight vertically, if we followed a line up there at the very top, the pressure is the atmospheric pressure. So the total distance that would travel up would be our pressure head. So this is visualized what they mean by hydraulic grade line or pressure heads. So yeah, so let's maybe can we redraw this? How can I add a page? Can you add a page in the middle? So what I mean by this, our pipe has a length of 50 meters and it goes from a height of 10 meters to 15 meters. So this is our pipe section 1. It has a distance Z1 of 10 meters. And it travels 50 meters, some distance, and it goes to section 2 with a Z distance of 15 meters. So if we were to put a pressure tap right at point 1, it would fill up to some point up here. H1 would be equal to P1 over gamma plus Z1. And that would be our hydraulic pressure head. And then we did the same thing at point 2. Let's just put a tap, open it up to the flow, and let the fluid flow up at that point. And we would get H2 which is equal to P2 over gamma plus Z2. So they're different than the actual elevation of the pipe. It's just referring to the pressure head that would be generated. So if we want to visualize pressure head, just imagine sticking a straw or something, a pipe, into your flow and seeing how high that flow goes up into your pipe. So the difference between these two try and draw that a bit better. The difference between these two is, in this problem, due to our friction losses. Does this make a little bit more sense? So when we talk about pressure head, we don't mean the elevation of the pipe itself. We mean the height of a fluid column that would give the same pressure as the pressure P1 over gamma plus Z1 in the flow. So where did you get 0.05 isn't the diameter of 2? Oh, yes. I think my mind was still on the last question. Yeah, sorry to confuse. Over here, the diameter is 0.2. So that might change our answer. So to add another note, if our pipe has an area A, perimeter would be equal to pi times d. And the diameter is here, so our area is pi d squared over 4. So new answer 0.03103. Eraser. 0.03103 would be 31 pascals. So yeah, hopefully that clears up a little bit. There might be some confusion. We're getting some answers around what pressure head means. And when we talk about friction losses in pipe, this is what we're discussing. So because the cross-sectional area of the pipe isn't changing, the velocity terms are gone. So everything we've done here is for a pipe section that has constant diameter. The geometry of the pipe isn't changing over some section of pipe. And for our diagram, if I draw one last length of the pipe is 50 meters. So yeah, the answer was 31.03 pascals. And the head pressure loss due to friction, we said, was 3.17 meters. So let's get to our just last section of applications of Bernoulli's equation. Sometimes we'll have branching conduits where we have one pipe splits into multiple sections, and we can apply Bernoulli's equation of the flow of the conduits as long as it's steady and incompressible flow still. So in this case, we have in this example, two streamlines. So at point 1, we have streamline 1 going to 2, and we have streamline 1 prime going to 2 prime. So we can write Bernoulli's equation along each of these streamlines, which is streamline 1 and streamline 2. And if we recognize that the streamline at 1 and 1 prime, so at point 1, if we have uniform steady flow, these streamlines are also equal. So P1 over gamma V1 squared plus over 2G plus Z1 is equal to P1 prime over gamma plus V1 squared prime over 2G plus Z1 prime. So these two are essentially the same for steady, excuse me, incompressible and uniform flow. So if that's the case, then we can write for a branching conduit, if we know at one value the Bernoulli relationship, then we know the relationship at any point. So we can just rewrite it in terms of our branch index n, where n is just the index of the branch. So in this case, n would equal 1, 2, 3, etc. So basically, we can apply Bernoulli's equation along any section of pipeline. So let's do a quick example with this. So here we have a somewhat complicated branching pipeline in the horizontal plane. So this is top view. So we don't have to worry about a change in elevation, which is nice. We have a 500 millimeter diameter pipe that branches into 3 separate pipes, where we have B is 100 millimeters, C is 250 millimeter diameter, and D is also 150 millimeters. The upstream pipe is designated as pipe A, and 3 branches of pipes are designated as pipe B, C, and D. So when the flow rate of the water pipe A is 450 liters per second, the pressure measured in pipe A is 350 kPa, the average velocity in pipe C is 3 meters per second, and the pressure in pipe D is 250 kPa. It's asking what is the volume flow rate in each of the 3 pipes, and then B, what is the expected pressure in pipes B and C? So where can we go from here? So what is the volume flow rate in each of the 3 branch pipes? Any thoughts? Where should we go? Let's start with just by writing some Bernoulli's equation. When in doubt, let's write Bernoulli's equation. So let's write PA over gamma plus BA squared 2G. There's no change in elevation, so we can ignore the Z terms. It's going to be equal to PB. Let's do PC first. PC over gamma plus BC squared over 2G. So we know pressure at A, we know the velocity at A, we know the velocity at C. So we can solve for the pressure at point C. So we know VA is equal to Q divided by the area at A, which is equal to 2.292 meters per second. So Q is given as 450 liters per second. And the area, we know the diameter, so we can calculate that. So we can solve for the pressure at C, and that is equal to pressure at C should be equal to 348 kPa. So that was the low-hanging fruit. That was the easy one. So we know the pressure at C. So we've answered B first. How can we find the volume flow rate in the three pipes? Because we don't know any information about point B, so we can't solve for the pressure in point B yet. There's too many things we don't know. So we got to figure out what is the volume flow rate through that section, and if we know the velocity, then we can use Bernoulli to solve for the unknown pressure. So yeah, good. So for continuity, we need to have the flow rate in section A has to equal to the sum of the flow rates in the other three sections. Since this little junction here isn't accumulating fluid, we must have continuity, which says that QA is equal to QB plus QC plus QD. So we know QA was 450 liters per second, so 0.450 meters cubed per second. QB is equal to ABVB. We don't know either of those values. QC is equal to AC plus VC. We know VC, 3 meters per second. So we know these, we know the area of B, and then QD, AD times VD. We know the area, we don't know the velocity. So we don't know VB, we don't know VD, and we don't know the pressure at B, but we do know the pressure at D. Pressure at D is 250 kPa. So let's use Bernoulli again to figure out that unknown pressure or that unknown velocity at point D. So let's write Bernoulli's equation from point A, PA, from A to D, PA over gamma plus VA squared over 2G is equal to P times D, or PD times gamma, 1 over gamma, VD squared over 2G. So this is 250. This is 350. We know VA is 2.292. So we can solve for the velocity of D, and we get velocity of D is equal to 14.34. So we now know the velocity at D. We know everything else in that equation for continuity, so we can go back to our continuity equation and we can write 0.450, so continuity. .450 meters cubed per second is equal to area of A. Diameter of A was 100 millimeters, so 0.1 squared over 4 times VA plus QC pi times 0.25 squared over 4 times the velocity of C is 3 meters per second squared plus pi times 0.15 and the velocity at D is 14.34. So we solve for the unknown VA at velocity at A or sorry, B. Sorry to confuse. So we solve for just that QB term. QB would be 50 liters per second. Therefore, QC would be equal to 147 liters per second, and QD is equal to 253 liters per second. We have the pressure at D, and we have the pressure at C. We could use Bernoulli's equation again to find the pressure at B. So if we know all these terms, simply substitute PB or solve. PB is equal to 333 kPa. So we have our flow rates through our 3 sections of tube. We have our velocity, our pressure at B, our pressure at C. We've answered all of our questions. So I'll scroll back down in a second, but just want to go over again the thought process for solving a branched system. Bernoulli's equation will let us solve for one unknown variable along a streamline for a branch system if we don't know the flow rates. We needed that continuity equation for a single pipe to be able to solve for 2 unknown variables like velocity and pressure at some other point. When we have a branch system and we don't know the flow rates in all the other 3 downstream sections, we can only solve for one unknown at a time. So if we measure, have enough information that we only have to solve for one unknown at a downstream section of pipe, solve for those unknowns first. So we knew the velocity in C, so we solved for the pressure. We knew the pressure at D, so we solved for the velocity. Once we know the velocity of both sections C and D, we can use the continuity equation now to figure out what the velocity or the flow rate is in B. So once we know the flow rate in B, then we know 2 equations. We know the continuity equation for the flow rate in B in terms of the flow rate at A, and we have Bernoulli's equation. So we can solve for the 2 unknowns at section B, which is the pressure and the velocity. So solve the sections of pipe that you have one unknown first, and then use continuity to figure out the section of pipe that you don't know. Let's just put that here. Solve these first. Yeah, the answer is 333 kPa. So I think that takes us to the end of our first section for today. So quote for the first section is, there is a virtue in work and there is a virtue in rest. Use both and overlook neither, which I think is the same quote I left you guys with last week. So I believe I now owe you a quote.